Hello everyone. Today we shall see some guidelines and principles and things to keep in mind when designing PCBs and especially for high speed or high frequency applications. So before we delve into what are the problems with high speed or high frequency PCB layouts, it is important to first understand the conventional PCB technology. So PCB stands for printed circuit board, and it is the final stage for any electronic circuit or system before it has to be applied or deployed in any dedicated applications. So whenever you look at the electronic circuit behind most of our domestic appliances, you will see that the circuit exists in the form of a PCB. Why? Because a PCB provides a permanent and mechanically and electrically stable connections. If you are going to use breadboards and wires, they would not last. So any wire could come off very easily. So a circuit board, a printed circuit board is not like that. So the way this PCB is designed, or rather how the connections are printed, how the components are arranged and kept on the PCB, they may have a lot of role to play, especially at high frequency applications or high speed applications, or especially which might be a point of interest for electrical engineers, high power applications. So the way we are laying out the PCB, that is called the artwork. So the way the artwork is designed plays a very important role in the functioning of the PCB. Now conventionally, a PCB has a minimum of two metal layers. Generally that metal is copper, and those two metal layers sandwich a dielectric. So the dielectric is generally some form of a glass epoxy silicon dioxide based compound, and there can be more than two layers also, but for this particular course we shall not look at those things. So now the PCB design or the artwork is all about using those copper sheets and doing some etching on them to remove the copper that we don't want and to keep the copper that we want. So the copper that remains on the PCB is nothing but the connections from one point to the other point which we want to define. So generally, conventionally, the two metal layers for the PCB, the names have been given as the component side and the solder side. Now this nomenclature was given during those days when PCB technology was not yet very well versed with surface mount technology. So in those days, most of the resistors, capacitors, ICs which we would use were through hole components, as you know well by now. So for that, what would happen was that the mounting would be done from one side and the soldering would be done from the other side. So because all those component packages would have pins which would be mated through holes, and the soldering would be done through the other side where the hole and the pin would come into contact. But nowadays surface mount technology has evolved so much that the component side and solder side names are very rarely used. So we normally call them as top side and bottom side, where both top and bottom side can be used for component holding or soldering, whichever. In case of surface mount devices, of course, the layer where the component is mounted is the same as the layer where the soldering has to be done. So now these definitions have become very loose. So some of or two of the most important types of PCB etching techniques, one is called as subtractive etching, the other is called as milling. So 80 to 90% of the applications of PCBs or the fabrications of PCBs make use of subtractive etching. Now what this is called, it is a kind of wet etching where the part of the copper that is not needed for the connections is totally removed. And what happens essentially is that the copper that you want to keep on the bare PCB, you need to cover it with a photoresist. So it is very similar to something called as lithography, which is used in VLSI technology. So the copper that you want to keep is covered by a mask or a photoresist, and then the copper that is exposed, which is not covered and that is intended to be removed, is then immersed in an etching liquid where a displacement reaction takes place and the chemical eats up that copper. So therefore whatever is the copper that is below the photoresist or the mask which you had covered before etching, that stays back. So therefore that way you have your connections. Now this is very attractive option, but the problem is often the amount of waste copper that is generated is sometimes a little difficult to dispose. Although these days it's not a major problem. Earlier it used to be a lot of problem. So the second technique is called as milling. Now milling is an example of dry etching. So there is no question of any liquid chemicals which are involved to eat away the copper. So what is done in milling is that whatever PCB you want to make, you first feed the board into a machine which has a number of precision cutters which separate the copper tracks that you want to keep for the connections and the excess copper by means of creating a ridge between them. So what happens is it just creates a ridge and it does not remove the excess copper. So that way it is a very economical technique, but there are a lot of applications, especially for high frequency and RF applications, where the excess copper has to be removed. So in such case, removal of excess copper is little difficult. So that is why milling is often not used. Once we reach the end of this presentation, we shall see some videos of milling and subtractive etching. So modern PCB technology, however, has tremendously evolved to help the designer a lot by including features like printing of text and legends or whatever you want to print for easy use of the PCB. Then there are techniques for rust and oxidation protection. So once we start using the PCB, the copper gets exposed and slowly it starts getting rusted. So therefore its performance degrades over time. So modern PCB technology provides you these techniques to prevent rust, and of course there could be, during the PCB fabrication process, there could be some inadvertent short circuit between two tracks which are not supposed to be short circuited. So therefore these sort of testing things are also incorporated by most PCB manufacturers, and overall the technology gives you an option to make your PCB look very good and identify things in the circuit very easily. Now the PCB design nowadays is not done by hand. Most of the PCB design is done by means of using some PCB design software. So now essentially what happens is the different aspects of a PCB is coded into something called as layers or masks. So, and every different layer is accorded a different color. So this is specifically I'm talking about Eagle, but that is the case with most other PCB design softwares too. Now some of the important layers I have mentioned over here which we shall consider. There are many other important layers too, but they are not as important as these 5. The first layer which we should consider is the component side and the solder side. So therefore the copper artwork that we are doing on the top and bottom, that is the connections or the copper configurations that we want to retain for the connections. That data in the two different layers is called as the component layer and the solder layer. Or by definition, you can also call it the top layer and bottom layer. Second is called drill layer. Now this is very important. It may so happen that you have a copper track connection running on the top layer, but that needs to be connected via the bottom somewhere. So therefore, a drill is required to connect the top and the bottom via the dielectric, which is sandwiched between the two layers. But then making a hole is not enough. You need to provide a physical metallic connection between the top and the bottom through the cylindrical hole. So therefore, this drill or the via, after drilling, is subjected to a process called as plated through hole, PTH, which is an electrochemical process where metal is deposited along the cylindrical vertical periphery of the hole. So therefore, this plating essentially ends up connecting the top and the bottom. Now this is a tremendously useful technology. Now it is very similar to something like vias which connect multiple layers in VLSI technology. Next comes solder mask. Now solder mask is provided by almost all PCB manufacturers. So to prevent the copper tracks from getting rusted, a thin film of insulating material is covered on the copper tracks to prevent them from rusting. Also, it reduces the risk of erroneous soldering, where some solder drops can get deposited on that copper by mistake. But if you have the insulating film, then that will not happen, because the excess solder would then just slide off. So of course, the solder mask is not covered everywhere. It has to be kept open in places where you want soldering or the connections with different components to be done. But the tracks which are not to be connected at points to any component, those are generally covered by the solder mask. So the places or the points which you want to keep open for soldering or component mounting or connections, that information is called a solder paste layer. So solder paste layer consists of those areas where the copper is to be left exposed. But then again, that adds the risk of rusting. So it is not kept open directly, but it is finished with a solder alloy on those parts, which not only prevents rust but also provides a better base for soldering. And the technology to finish those copper with a solder plating is called as hot air leveling, or HAL. And finally, you have something called as a silk screen layer or the silk screen data. So this consists of the text that you want to print with the PCB. For example, you might want to label different components as R1, C1, L1, L2, like that. Those layer will be printed. If you want to put a copyright of your name on the PCB, then you can print your own name on the PCB. But those will not be printed in copper. They will be printed with a different ink. Now, apart from the components layer and the solder layer and the drill layer, the solder mask, solder paste and silk screen layers are made for both sides, the top as well as bottom, because nowadays you can have components on both sides. So the information for all these 5-6 layers, what we just discussed, it is totally called as Gerber. The Gerber data is what you must send to the manufacturer once your PCB design is complete. So an example, you can see over here, the copper tracks are covered with this green film, that is the solder mask. But over here you can see a number of wires where the resistors have to be soldered, and over here the IC pins have to be mounted. So over here you can see it's a different color. Those coppers are are exposed and they are finished with HAL. So also you can see a number of text is printed, IC1, R36, R37, like that. So this is an example of the silk screen layer where the text is printed. So now, how do you get started with designing PCB? Now PCB is to be designed once your circuit is ready, your design is ready, and you know that your design is working. You must have tested it either through a breadboard or some simulation. So the first thing to do is to create a schematic. Now the schematic is a blueprint for the PCB. It looks just like any circuit simulator where you have components and their interconnections. Now obviously how to make the correct connections you will know. You must have read the datasheet of the different parts before you make the schematic. Now try to include as much information as you can in the schematic, because later on if there is somebody else who is using the schematic for their own purpose, they may not be immediately familiar with what you are trying to do. So these notes will be very critical or useful in helping them. So for example, if the schematic can include information about different packaging of the ICs that are used in the design, then critical component placement. There are some components have to be placed away from the others, for example, to avoid heating effects. Tuning or alignment, this is very important. If there is some tuning element or the alignment of the components have to be done in a particular manner. Then things like thermal issues, points which on the design which could pose a thermal problem, which could get heated up very easily. So that information you must give. And if there are some impedance lines which are controlled, for example, characteristic impedance of transmission lines on the board, so those information would be very useful. There is a lot of other critical information also which you can give, but I have not mentioned them explicitly over here. So this is an example of a good schematic. You can see that most of the connections are shown over here, but in red colors a lot of notes are put. So this is how good schematic is to be made. And at the bottom also you can see how different notes are put in black color. Now once your schematic is ready, we have to convert that schematic into the layout or the artwork. So there are three things in doing PCB design which you have to keep in mind, that is planning, placement and routing. So just like real estate, your PCB area can be thought of as a piece of land on which you need to do the most optimal work that you can. So think of it as real estate. There are applications where the size of the PCB should be as small as possible, and within that constraint you have to sort of do your work. Now the first thing, planning means before you make the layout there are certain things you need to have in mind. Things like at what position of my PCB should my power supply connections lie? At what point should my inputs and outputs lie? Should I place them all on the same side or on different sides? You need to think of how the PCB is to be used, and that will tell you a lot about how at least these things are to be connected, or at least the interfaces to the outside world. For example, the inputs, output signals, the power supply connections, so on and so forth. At this stage for planning, what is inside the PCB that is not of prime importance, that comes in the second step, that is placement. Now placement has to be done in such a way that ideally every two components must be connected through the shortest path possible. So the shortest path means least resistance, so therefore it is a very attractive approach. But there there can be certain times, times when the shortest path may not be able to serve the correct purpose. So for example, if you have an input to the PCB which has to be connected on the edge of the PCB, but suppose that input signal will go to an amplifier which is kept somewhere in the center of the PCB, and the amplifier's position cannot be changed because all the other connections are the shortest path. In that case, you have to make a long track from the edge to the amplifier input for the signal, and in that case you have to be extra careful. Now that is what I would call as a critical path. So paths, connection paths from one point to the other point in the same layer or through multiple layers is called as routing. So once your connection is defined, converting those connections into copper tracks is called as routing. So you need to think of what is the best path for the copper track to connect the 2 points. Should it stay far away from other parts of the circuit, or can it go through a crowded component area? So these are the things you need to think of. Now this is an example of very poor placement and poor routing. Immediately what you can see is that the power block, which is driving almost every block on this PCB, is kept in the corner. So as a result, the connector and the digital blocks, they are very, very far away from the power input, and as a result they have to travel a lot of distance, and you can see that they are going through a number of common paths. So in a number of places the red and black are sort of intersecting. So in that case, these lines can pick up noise from the other lines. So therefore, it's a very bad approach, and if you have noise on the power lines, then definitely your circuits or those blocks are not going to work optimally. So a better way to do this placement is this way, where you are placing the power block in the center. So now you can see that the connections are much shorter and there is hardly any overlap, and therefore the noise can also be reduced in this way. Now the first thing to do while during the PCB layout is check all the data sheets of the different ICs that you're using. Many times in data sheets they will also tell you some guidelines on how to design a PCB for this particular IC. So follow those. Now fix the locations of all the connectors. Maybe they are for signal, for power points, whatever. So some connectors for interfacing external components, some connectors may be there for connecting wires from one point to the other depending on the application of the circuit. Now remember that if an IC gives you a choice of using different packages of the same IC, then remember, as we discussed, smaller IC packages are used for high speed and high frequency, less parasitics and a more compact layout. Larger IC packages are used for more general purpose applications and also ease of soldering. So please be careful. I am not telling you to use either small or large because you are the designer. Now these decisions have to be made by you. Then proper connections of power supply and ground lines, which I just mentioned a few minutes back with those placement figures. So power supply and ground lines have to be designed with minimum resistance. So, and obviously as short paths as possible. So shorter paths mean lesser resistance, but there are times when we have to use longer paths too. But are they always bad? Well, we have to see that. So there are some critical conductors like transmission lines and sensitive tracks which are carrying signals which should not be affected by noise. So these critical conductor lengths you need to keep as low as possible. Now if there are an array of components which you are using in your circuits, then we should follow the convention of same orientation and direction of mounting those components. Most importantly, in your layout, you should always give the facility that after soldering or after mounting, you should be able to access some test points so that troubleshooting becomes easy. Then if there is some need to do some component replacement, it can be done easily. No two components should sit one on top of each other. In that case, replacement of the below component would be difficult. So therefore, replacement feature should also be there. Now, last but not the least, you should separate the heat sensitive components from those components which are likely to produce heat. And for those components which can get heated up, you need to provide heat sinking solutions on the board. So one thing you need to see, I was just mentioning about what is the bad thing about long tracks, or are long tracks always bad? So there may be sub blocks in your circuit or your PCB where you are using both analog and digital blocks. In such a case, it is very, very important to isolate their VCC paths as well as the ground paths. If you keep the same return path for the ground, then it is very likely that due to the proximity of the connections, noise on the analog ground may affect the digital ground. So if you look at the second figure, it is better. They are isolated in a more better way. So here what we are doing is, even though the line becomes longer, they are actually helping in isolating the two sub blocks. So the noise contribution in these return tracks happen because of the resistance of the conductors and also some parasitic inductance. So therefore, these are the things we should keep in mind. The analog and digital grounds should always be isolated. Now comes signal tracks. Now, for example, signal tracks, they are the most vulnerable of tracks on the PCB. Now, one of the most important drawbacks which signal tracks can face is crosstalk. Now, let us say you have an amplifier which gives you a gain of -A. Then in that case, what is happening is that the VI and VO, they are of opposite polarity. When VI reduces, VO increases, and vice versa. So now, if the input and output lines of the amplifier are close by, and VI and VO are switching in opposite directions, then a parasitic capacitance can form between those two lines, and that is called as capacitive crosstalk. So this can happen, as I mentioned, when the two inputs, the two lines, the input and the output, are physically close to each other. So you have to be very careful in seeing this. The overlap should reduce. The other kind of crosstalk which can happen is inductive crosstalk, which exists due to the magnetic field interaction between long running parallel traces. So if you are having signals, try to reduce overlap, or try to reduce the distance for which multiple tracks are running in parallel. This way you can reduce the inductive and capacitive effects. Now, when you are using signal tracks, routing signal tracks, there will obviously be time when you have to bend. The bend should be preferably circular, or the angle for the bend should be between 120 and 180 degrees, and avoid 90 degrees or something below it. Why? Because the more sharper the turn becomes, the more is the discontinuity, and therefore this can lead to impedance mismatch and reflections, specifically for high frequency signals. And remember that if there are very, very long tracks carrying high frequency signals, the size of that track can be comparable to the wavelength, and therefore those lines could also start behaving like a bad antenna and start radiating, and that's the last thing you want. So I mentioned, minimize long parallel track pairs that carry AC signals. So, but if the signal tracks are on different layers, it is even more critical that you separate them, because it should not so happen that one track is running on top and another parallel track is running on the bottom. You can use ground planes or guard tracks in between two parallel tracks. This reduces the coupling or the capacitive crosstalk by a fair amount. So a ground plane is nothing but a conductor which is connected to ground that is spread over in some different shape across the PCB. So what is ground plane? We shall see when we are seeing the demo of the design software. And of course, using differential mode signaling for transmit receive pairs can prevent not crosstalk but different pickup from external elements. So what happens is, if you have differential signals and there is some common noise which is affecting both the tracks, so then at the receiver you can simply take an inversion of one of the differential lines and add them. So the signal will retain but the noise will get cancelled out. Now, power supply and ground bounce. This is a very critical thing which can happen if your power supply VCC or ground become very thin and the inductance starts taking effect. Now what happens is, this can happen generally for digital circuits. Suppose I have a simple NOT gate or an inverter which is connected to a VDD line and a ground line, both of which are very thin. Now at the input of the NOT gate, I am giving a square wave, and during the transition, when the inverter is trying to switch, now because of the finite impedance on the VDD and ground lines, the inverter is providing a very low impedance path. So therefore, to balance it out, there will be either a spike or a drop in the power supply line, and this is called as bouncing, and it's very, very bad. It can cause degradation in performance of your circuit, in this case the inverter. So to avoid this bounce, we generally try to keep the width of the ground and VDD tracks the highest. This will ensure lowest resistance, lowest inductance, and therefore low probability of bouncing. So generally, a good convention to follow is the ground width should be the biggest if we are using it as a ground plane. Next comes VDD width, and these two should be much more than the signal track width. So you can use the ground plane. If you want, you can use the VDD plane also. But very important thing to see is that connect the top and bottom tracks for supply and ground through multiple wires if possible. This is especially when you are going for high frequency signals. So having multiple wires helps in reducing the overall inductance. Now very importantly, use something called as decoupling capacitors. Now decoupling capacitor is a capacitor which you need to use in parallel with the power supply line and ground, which is generally kept very close, physically close to the IC supply. So for analog circuits, these decoupling capacitors, they provide low impedance for AC ripples. Okay, and for digital circuits, they provide the local charge supply for fast rising and falling edges. So therefore, this in case of digital circuits is able to somewhat reduce the bouncing effects. Now, most applications require a minimum of 2 decoupling capacitors kept in parallel as close to the chip as possible. Now, why do we keep 2 decoupling capacitors in parallel separately? That is something you need to think about. And use surface mount devices for high frequency circuits. That is obvious. Now, coming to eagle, there are certain layers which we need to keep in mind. Now, these layer numbers I have written over here. Some of these are processed for fabrication. Some of these, even though they are not processed, they are important. So I would request that you please keep track of these layers. With time, you will know which layers to keep track of. So the first layer number 1 and 16 are for top copper and bottom copper with the solder mask. 44 and 45 are for drilling. 18 is for the solder mask for the wires which you have to use for top and bottom. So both top and bottom, that solder mask has to be there, where the finishing is done through the alloy. So these 4 layers are processed and are used by the PCB manufacturer. Then comes unrouted, layer number 19. Unrouted is not processed, but will tell you if you have forgotten to cover or if you have forgotten to convert any electrical connection into a copper track. We shall see this very shortly. Then comes dimension. What is the outline of your board? There is a thin white line, generally square or rectangular, which will tell you that the board size is so and so. That's a boundary. Then 23 and 24. That is the component origin point that exists in both top and bottom. 23 for top, 24 for bottom. That is the point through which you can move or rotate components. 25 and 26 are for component names. Suppose IC1, R1, C1, L1. Those are component names. 25 and 26 for top and bottom respectively, and this is processed. 29 and 30 is the solder mask or the solder paste for non-wires or the points at which you want to solder components, and that can happen for top and bottom. 29 is for top, 30 is for bottom. Now 39 and 40 are the top and bottom layers for keep out. Now keep out is a line that exists around every component, kind of as a Lakshman Rekha, so that no other component must breach that line and come inside. That means that keep out line is designed to sort of maintain adequate distance between two components.